Hello, my fellow causal champions. My name is Dan Harris, and I'm your host today on Causal Discoveries. In this episode, we continue this series investigating the theory of universal specificity, which directly challenges the venerated theory of relativity. Be sure to subscribe below to keep informed as to when new episodes in this series are released. In our last episode, I made the bold claim, as way of an analogy, that relativity is to the geocentric planetary model, as universal specificity is to the heliocentric planetary model. I then outlined 5 parallels between Kepler's work on validating the heliocentric over the geocentric model, my work on validating universal specificity over relativity, which is covered in this series. Check out that episode linked below to get the full discussion. In this episode, we have 3 guest speakers lined up to help us cover the first 2 parallels, which focus on describing 2 competing models, each based on 2 very different assumptions. I hope you enjoy this episode on Causal Discoveries. You may be interested to learn that the thoughts and experimental data laying the foundation for relativity began over 100 years ago when trying to settle the great debate over whether light was a wave or a particle. The group that thought light was a wave postulated that, like other known waves, light too must travel through some medium. And what you might now consider empty space was then thought to be something called ether. Ether was essentially considered a canvas for light to exist in and travel through. Additionally, this group thought that, like other waves traveling through a medium, light's speed relative to that medium must be constant. Therefore, it was concluded that objects traveling through the ether must experience a different speed for light relative to itself, which could be tested through experimentation. That experiment, called the Michelson-Morley experiment, is where it all began. And this brings me to introducing our first guest, who received a Nobel Prize in 1907, in large part due to the results of this experiment. And I also feel compelled to mention that he is a fellow graduate of my alma mater, the United States Naval Academy, class of 1873. Today, you can find Michelson Hall, an academic building at the Academy named after this guest, which houses one of his interferometers, akin to the one used in this experiment we'll soon be discussing. Please help me give a warm welcome to Albert Michelson.
Thank you. I'm glad to be here.
So, Al, may I call you Al?
No, Dan, you may not.
No? Oh, excuse me. What can I call you then?
You can call me Commander Michelson, or Sir. You know, my sources tell me you're still in the Marine Corps Reserves. Are you not, Major?
Yes, sir. At least for another month or 2, until my resignation paperwork goes through. I guess my sources need to do a better job of informing me at which point in my guest's history they were being pulled from.
I'm just pulling your chain, Dan. From one field grade to another. Just call me Albert.
Okay, Albert. You had me worried there for a second.
Yeah, you should have seen yourself sweating there for a second and taking it out on your poor research staff.
Well, Commander, Albert, would you please inform my audience about the nature of the Michelson-Morley experiment, its purpose, method, and results?
Of course, Dan. Let's start with the basics, right? This 1887 experiment was intended to detect the ether, that medium postulated to exist such that light might travel through it as a wave. Now, we ran this experiment on many sources of light, okay, in the form of stars, different directions from Earth, right? And so we tested these different stars, and this is just an example of one of them. They're very far away, which, again, they emit light in all directions, but when it gets to us, the light that gets to us is very straight from that same source. And what we wanted to do was measure at different points in Earth's orbit. Okay. Now, the reason for this is, and here's our sun. The reason for this is we wanted to vary our speed relative to the ether as much as we could. And in this setup, the average speed of Earth in its orbit is 66,000 miles an hour, and so it would be going 66,000 in this direction and 66,000 miles an hour in that direction, giving us a total of over 130,000 miles an hour difference. And that's plenty to be able to detect a difference in the speed of light coming from this source. So
that would, if we did succeed in detecting a difference in the speed of this light from the source, then that would be a successful detection of this ether that was postulated to exist. But alas, the results of this experiment was that the speed of light did not change. Wow, that is a shocking result. Our next guest will go into interpreting these results, but could you please briefly and simply describe how you measured the speed of light?
Sure. Yes, of course. Yeah, it's slightly more complicated than this. Link below for full details. But essentially, it involves a stopwatch and a mirror. All right, the light's going to come in from the source, like so. It's going to pass a stopwatch. Let's say here, it's not drawn to scale or anything. And that's going to start our time hack. Bounce off this mirror. The light's going to return to our stopwatch and pass through. And this is going to be the end of our time measurement at that point. Again, when it passes the stopwatch again. So it's going to clock start, clock stop. All right, start, bounce, stop. And that's going to give us two critical pieces of information, this contraption. It's going to give us the time it took, and we're going to have this known distance as well. Right? So this is going to be our known distance. And velocity is going to be measured the usual way, where it's change in distance over the change in time. Now, you can do the math yourself, and I'll just show pictorially real quick. But if this contraption were moving relative to the ether, then it's not going to make this straight up and down movement, right? It's going to, let's say it's moving sideways. The starlight's going to come in from an angle, it's going to hit the mirror, it's going to bounce out like that. So basically at t0, your watch is going to be here, but your watch is moving with the velocity, with the device we're using to measure. The mirror is going to be slightly to the right because it's slightly further in the future. This is going to be moving with the velocity. And then you're going to measure your second time here. All right, you can see that this distance, making this V shape, is going to be bigger than the distance just if it were just going to go straight up and down. But you can do the math yourself if you're not convinced.
Oh, now that's interesting. So you didn't measure the one-way speed of light to the mirror. You measured the average speed of light that went to the mirror and then back again.
Yes, that's correct.
And it's this average that appeared not to change.
You got it, Dan. That's correct.
Okay. Wow. Amazing work, Albert, inventing such a device that was crucial for making measurements necessary for future causal discoveries. Thank you very much.
You're welcome, Dan. I'm sure if it wasn't for me, someone else would have done it. Everyone was working on this problem at the time.
He's just being modest, folks. Man, what a great experimental physicist. Albert Michelson, everybody. All right, to help us make sense of these strange results, let's welcome our next guests, Hendrik Lorentz and Albert Einstein.
Thank you.
Okay, starting with Hendrik. Can each of you, using your various theories, help the audience make sense of the Michelson-Morley experiment full results? And please be sure to list the base assumptions as well.
Sure. To begin, the Lorentz ether theory assumes there is an ether, and light travels through this ether at constant rate in all directions relative to the ether. While light is not constant for other reference frames moving within the ether or relative to the ether, light might move faster in one direction and slower in another. Much like in air, sound moves constant in all directions in the air, but a moving plane might sense that sound travels faster relative to it in one direction and slower relative to it in another. So making sense of the experimental results of Michelson on this foundation, then one must conclude the average two-way speed of light only appears to be constant due to the miscalibration of instruments. The two-way speed of light is not truly constant because of a phenomenon called time dilation and length contraction, which causes this miscalibration I speak of. Yes.
Thank you, Hendrik. That makes good sense. What about you, Albert? How do you go about explaining the Michelson-Morley experimental results? And please be sure to list your assumptions as well.
According to the theory of relativity, there are two fundamental postulates assumed to be true. The first, the laws of physics are the same and can be stated in their simplest forms in all inertial frames of reference. The second, the one-way speed of light is constant in all frames in all directions, independent of the relative motion of the source or the receiver. From there, making sense of the experimental results of Michelson becomes easy. The average two-way speed of light appears to be constant because the speed of light is constant in all directions, regardless of the Earth's motion.
So, the phenomena of time dilation and length contraction do not come up under relativity.
No, time dilation and length contraction are a consequence of these two postulates as well. Transformation between space and time occurs when comparing measurements from one inertial frame to another.
Really? Does this transformation have a name?
Yes, it's called the Lorentz transformation.
The Lorentz transformation, as in Hendrik Lorentz.
Yes!
Hendrik, does a similar transformation exist in the Lorentz ether theory?
Yes.
Huh. Could you both please write down your respective transformations?
Sure.
They look exactly the same. Am I missing something?
No.
How is this possible?
Well, you go ahead, Henry.
Oh.
You go ahead, my dear. Oh, thank you, Al. Oh, I appreciate that very much. When you assume the average two-phase speed of light appears to be constant for any inertial frame, this transformation falls out. Whether light only appears to be constant because of miscalibration as assumed by Lorentz ether theory, or it's truly constant in all directions as assumed by relativity, regardless, you get the same transformation.
But light appearing to be constant and being constant are two contrary assumptions. Is there at least a difference in how each theory uses or perhaps interprets this transformation?
Yes. Sure.
Oh, good. Please explain this difference.
You go ahead this time, Al. You go ahead. Thank you, Henry. The first thing you need to realize about this difference is that infinitely many inertial frames exist on a continuum. The Lorentz ether theory assumes only one is universally stationary relative to the ether, while relativity assumes any one of them could be considered equally stationary. In other words, relativity says no universally stationary frames exist. So relativity uses this transformation to compare measurements from any one inertial frame to any other, while Lorentz ether theory uses it to go from the universally stationary frame to any other inertial frame or back again.
So, Hendrik, which frame is universally stationary?
I don't know.
You don't know. What do you mean you don't know? How is Lorentz ether theory useful at all without knowing which frame is universally stationary?
Your frustration is understandable, but it's for naught. As it turns out, because this transformation falls out from assuming the average round-trip speed of light is constant, then so long as you set any frame as universally stationary, akin to selecting a ground in circuit analysis, then so long as two or more objects start and end at the same location, essentially making a relative round trip, then you can determine the proper transformation to compare how each object would make measurements. So you can predict the observations. Therefore, applying the transformation as though relativity were true to predict what you would observe is a kind of mathematical trick to get around not knowing which frame is universally stationary.
I see. So the verifiable predictions of relativities, those involving round trips, falls out from Lorentz ether theory?
Yes!
And one theory assumes the one-way speed of light differs in different inertial frames, and the other assumes it's the same?
Yes!
Why not just measure the one-way speed of light to see which assumption and therefore theory is correct?
Yeah, why didn't we think of that?
Think of that?
You can't.
You can't.
What? Why not? Oh, no, wait. Let me guess. Because you need two synchronized clocks in two different locations to start and end the time, and because of time dilation and length contraction, you can't synchronize them.
Yes.
Yes.
Okay, that actually makes sense. But just to summarize, the Michelson-Morley experiment failed to detect a change in this average two-way speed of light in different inertial frames, and two hypotheses based on two contrary assumptions are equally plausible. Either A, the average speed of light only appears to be constant due to a miscalibration, or B, light is constant in all inertial frames in all directions. Okay. Either way you go with these assumptions, the Lorentz transformation falls out, and both theories agree on all verifiable predictions, like which twin is older in the twins paradox, and they disagree on many unverifiable predictions, like the one-way speed of light differs in different inertial frames and there being an existence of a universal stationary frame or not. Did I miss anything?
No, you pretty much nailed it.
Okay. Thank you, gentlemen, for joining me in this episode on causal discoveries and for laying the foundation necessary for future causal discoveries.
You're welcome.
You're welcome.
Hendrik Lorentz and Albert Einstein, everyone. Wow, impressive work from both men. I feel way more educated than before about how relativity parallels the historical lessons learned from Kepler's experience. We can see that relativity is based on one assumption, and the constancy of the speed of light, and the Lorentz ether theory is based on a contrary assumption, which is the light speed only appears to be constant, but is only constant in this universally stationary frame. And both make the same exact verifiable predictions, which completes the objective for this episode. And recall from the first video in this series that this only partially covers the second parallel, because Lorentz ether theory does not extend into a theory of gravity. So we leave the completion of that coverage for a future video after covering the cause of time dilation, because only then can we dive into a new gravity model. But up next, however, one of our previous guests will be returning to help me cover the third parallel, where we analyze relativity, which reveals an anomaly that can only be resolved if its contrary assumption were true. Till then, you can review the status of the series production by referencing the WordPress link below, and that captures the draft outline of this video series and the progress of its development. Don't forget to like, subscribe, and share if you enjoyed this episode, and please add your comments or questions below. We want to hear from you. I'm Dan Harris, and until next time, enjoy making causal discoveries.
Let's go. Yeah. I'm like an addict, do I gotta have it. I ain't even playing, got a really bad habit. If it moves, gotta grab it. Fuse like a magnet, lose, won't have it till I'm doomed in a casket. I ain't playing, got a weird mind. If you work 8 hours, I'ma work 9. If the shoot tastes sour, you should taste mine. I'ma stay in power for a long time. Get up, nah, I ain't a quitter. Toss me the ball, I'm a really big hitter. Big picture, I'm a straight killer. Rising the song to the highest bidder. Got juice, got gas, I'ma move fast. New shoes, new tracks, like who's that? I'm new, come back, better than last. Yeah, it's a new me, never gonna look back. I'm never gonna look back. Cause damn, I was built to last. You You move slow and I move fast, and that's facts. Only I can make a change, slowly take a step